Well, today we have a very special guest. We have perhaps one of the most renowned physicists on the planet, someone who has been a proponent of science education in all of its different fields, but particularly in his own field of physics. He's the author of the current New York Times best-selling book, The God Equation, which is all about string theory. We have with us Dr. Michio Kaku. How you doing?
Very good. Glad to be on the show.
Yeah, it's great to have you on. And Dr. Yu and I, we do a program where we look at science news together. And of course, you're always in the headlines. So it's a great honor and a privilege to have you on the program to discuss your latest work.
Well, thank you.
So let's start off with the basics. You know, the God equation. People talk about the God particle. They talk about the God equation, these different concepts. What do you mean here when you talk about the God equation?
Well, it all started when I was 8 years old. A great scientist had just died, and the newspapers all published a picture of his desk, just his desk with an open book. And the caption said, "The greatest scientist of our time could not finish this book." Well, I was floored. I said to myself, why couldn't he finish that book? Why didn't he ask his mother? Why didn't he go to the library? What's so hard? So I went to the library over the years, and I found out this man's name was Albert Einstein. And that book which captivated my imagination, was to be the God equation. That is a theory of everything. We're talking about the holy grail of science, to find a unifying principle, a unifying paradigm, a unifying theme that could unite all the rich varieties that we see in the universe today. In other words, an equation that would allow us to, quote, read the mind of God. Well, I was hooked. I said to myself, I have to know more about this man and this God equation. So when I was in high school, I built an atom smasher, a particle accelerator, a 2.3 million electron volt betatron particle accelerator in my mom's garage. It consumed 6 kilowatts of power, created a 10,000 Gauss magnetic field. And every time I plugged it in, I blew out all the circuit breakers in the house. So my poor mom, she'd come home after a hard day's work and say, "Where's the fuse box? And why couldn't I have a son who plays baseball? Why not introduce him to basketball? And for God's sake, why can't he find a nice Japanese girlfriend? Why does he have to build these machines in the garage?" Well, I went to the National Science Fair in Albuquerque, New Mexico as a high school kid. And I met atomic scientists like Edward Teller, father of the hydrogen bomb. And they took an interest in me. And they said, "We're going to fund your scholarship to Harvard. We're going to make possible your career as a physicist." So this was a dream come true. And then later, of course, Edward Teller wanted me to work at Los Alamos National Laboratory. Doing what? Designing hydrogen bombs. Well, I gracefully and politely declined this generous offer to work on hydrogen bombs because I wanted to work on something even bigger than a hydrogen bomb. I wanted to work on the Big Bang. That is, the God equation set the universe into motion. We are consequences of this one unifying principle, and when it exploded, all the pieces became the stars, the galaxies, the planets that we see around us. So if you understand what happened before the Big Bang and why it started, then you understand the God equation. An equation perhaps no more than 1 inch long that will summarize the entire universe of equations. That to me is amazing. And that's what I do for a living. I'm the co-founder of string field theory, one of the main branches of string theory, which is the leading candidate for the theory of everything.
Now, now the equation, is this something that you're currently working on, or you believe you have that equation that you referred to?
We're working on it. We have two things to unify. One is strings. We think that all the subatomic particles are nothing but vibrations on a tiny, tiny little string, but also membranes as well. Now, the God equation for strings, that's my equation. I'm the creator of string field theory, which allows you to summarize all of string theory in an equation about an inch long. But now we have membranes, and some of the brightest minds on Earth now are trying to write a field theory of strings and membranes, and so far, no one's done it yet. So if anyone out there is listening to this radio broadcast and they want to find the God equation, let me give you some word of advice. First, tell me first. And we'll split the Nobel Prize money together, you and me, and we'll go down in history as the successors to Einstein.
Wow. So this is really high stakes stuff. I mean, this is reality defining stuff here.
That's right. And some of the greatest questions, unanswered questions in science, will be answered by this theory of everything. Like, for example, what happened before the Big Bang? What's on the other side of a black hole? Is there a white hole on the other side of a black hole? Are there other dimensions? Are there parallel universes? Are there gateways, wormholes to these other universes? And all these questions, like time travel, cannot be answered within Einstein's theory. You need a theory of everything to answer these cosmic questions, like, why are we here at all?
Now, we've had on the program before a physicist named Sabina Hassenfelder, she's got a book out called Lost in Math. And she says that there's an attempt to be too fixated on the elegance of equations rather than, the actual reality of physics. What would you say to that line of thought? Does that have any bearing into this discussion?
Sure does. First of all, I think that elegance and beauty, all great theories turn out to be beautiful and elegant, but not all elegant and beautiful theories turn out to be reality. So a piece of the set of beautiful, elegant equations is the God equation. So you can't throw the baby out with the bathwater. You see, what is beauty and elegance? To a physicist, beauty is symmetry. And symmetry is when you take an equation and you rotate it. You rate the components of this equation and it remains the same, like a sphere. You rotate a sphere and it remains the same. You rotate an ice crystal, it remains the same. You rotate a kaleidoscope, it remains the same. Now, if you have a theory of everything, what's inside this equation? The universe. And you rotate it, and what do you get? The same universe. There's only one theory which can do this. That is string theory. String theory takes all the particles in the universe, rotates them, and the equations remain the same. And as I mentioned, for strings, not for membranes, but for strings, that's my equation.
Now, what about membranes? Is that a difference? Is that a challenge to what you're working on, or it complements what you're doing?
Well, it turns out that in 10 dimensions, which is the dimension that I usually work in, strings dominate the universe. So string theory by itself is fine in 10 dimensions, but there are 5 string theories in 10 dimensions. Now we realize that if you go to the 11th dimension, there are membranes, and one supermembrane gives you all 5 string theories. So we now realize that 11 dimensions is where all the action is. There's only one equation in 11 dimensions, not 5. In 10 dimensions, there are 5 equations, of which I wrote all 5. But nature is a little bit more sophisticated than that. So in other words, we think that if you go to a higher dimension, there's more room to fit all the equations. You see, in 3 dimensions, if you try to merge gravity with light, with the nuclear force, they don't fit. You can try as you hard with a hammer. You cannot hammer gravity into light, into the nuclear force in 3 dimensions. In 10 dimensions, they fit together like a jigsaw puzzle. They just fit beautifully together. And this is what I call beauty, elegance, simplicity. Now, some people say that's not enough to be a theory of everything. Yes, but that's a requirement. That's a requirement. All great theories are beautiful, elegant. In fact, my favorite Einstein quote is, unless a theory can be explained to a child, the theory is probably worthless. Now, what does that mean? That means that all great theories are based on a simple principle, a simple paradigm, a simple picture. beautiful, elegant mathematics that represent a picture. All great theories are like that without exception. There's no exception to this rule. And again, that doesn't mean that a beautiful theory is correct. It just means that all correct theories are beautiful.
How would you explain membranes to a child? What is the definition of that?
Think of a beach ball. When you throw a beach ball into the air, you can play with it. It vibrates. It vibrates at different frequencies. And if you make it into a sausage, if you squeeze it and make a beach ball into a squash sausage, and you stretch the sausage long enough, it becomes a string. And so if you have a membrane, you can actually derive strings from a membrane by squeezing the membrane.
Well, very interesting. Now, the last 2020, you are someone who spends a great deal of your time engaging with the public and doing a public service by engaging all kinds
I
of
try.
popular audiences. But this last year, of course, there was a lot of that being shut down. So in the last 2020, did you have some time to, with that quiet, to spend time and break through some new insights into your work?
Well, let me tell you a story. In the year 1666, the Great Plague hit London. 1/4 of the population died in London as a consequence. There were dead bodies scattered all over the streets of London. Cambridge University was shut down, and a young 23-year-old man was sent home because it was lockdown. All of England was being locked down. So he was walking on a country road one day, and he saw an apple fall. And then he looked up, and he saw the moon. And then he asked the question for the ages. If an apple falls to the ground, does the moon also fall? And then he realized, my God, the moon is in free fall. And then he tried to find the mathematics necessary to calculate the falling moon. And there was no mathematics powerful enough. So what did he do? He invented calculus to calculate the motion of the falling moon. And who was this man? Isaac Newton. And what was the consequence of the plague of 1666? The Industrial Revolution. He worked out mechanics. You could use mechanics to find the motion of a cannonball, to find the motion of a rocket, to find the motion of bricks in a building. In other words, locomotives, steam engines, factories became the norm in England because Isaac Newton helped to set into motion the Industrial Revolution. So in other words, he didn't waste his time during the Great Plague of 1666. He went on to lay the foundation of what we call modern society.
Wow. Now, is Sir Isaac Newton your favorite physicist of all time, or do you have another?
Well, I think number 2, of course, would be Einstein. Einstein then took the calculus of Newton, generalized it to 4 dimensions, generalized it to curved surfaces, and out pops out general relativity. However, I should caution you, it turns out that if Einstein had never been born, we would have discovered general relativity anyway as a byproduct of string theory. You see, string theory says the lowest vibration of the string includes all of Einstein's theory of gravity. So if Einstein had never been born and string theory was born first, we would have gotten general relativity as nothing but the lowest vibration of a tiny string. So let me explain. If I had a super microscope, I could see that an electron is not really a dot. All textbooks say that the electron is a dot. Not so. We think that it's a rubber band. And if you twang the rubber band, it vibrates at a different frequency. So we have to call it a different name. The same electron vibrating at a different frequency, we have to call a neutrino. You twang it again, it turns into a quark. All the subatomic particles are nothing but vibrations of the same string. So what is the notes on a musical scale? Subatomic particles. What is physics? Physics is the harmonies you can make on vibrating strings. What is chemistry? Chemistry is the melodies you can play when these strings bump into each other. What is the universe? The universe is a symphony of strings. And then what is the mind of God that Albert Einstein spent 30 years of his life chasing after? The mind of God is cosmic music resonating through 11-dimensional hyperspace. That is the mind of God.
Now, string theory unites quantum and relativity. Do you think one is stronger than the other? Is relativity stronger in your mind than the quantum side? Are they both equally robust and strong?
Well, first of all of biology can be explained in terms of chemistry. All of chemistry, in turn, can be explained in terms of physics. All of physics, in turn, can be explained by two theories: the theory of the big, like relativity, black holes, big bangs, and the theory of the very small, transistors, lasers, particles, atoms. And these two theories summarize all physical knowledge, but they hate each other. They don't like each other. Why would God make a left hand and a right hand that don't talk to each other?
Yeah.
That's ridiculous, right? Whoever heard of a left hand and a right hand not talking to each other? But that's the problem. That's why we think there is a unified field theory. It's hard to believe that Mother Nature could be so disjointed as to create a universe with a left hand and a right hand that don't even talk to each other. That's stupid. So that's why I think there really is a theory of everything out there.
I want
And
to
they're
let Dr. Yu
equally
jump
important.
in. I've been asking the question so far, but
Okay. So yeah, that's a very good explanation. So you mentioned about the general relativity have a good predictions, include the quantum mechanics in their big world and small world. However, so based on the current formulation, so they are disconnected. How did your string theory connected both of them these theories?
So how does string theory tie together relativity and the quantum theory? Well, let me explain. Einstein thought that general relativity was like marble, beautiful, elegant, smooth marble. That's what Einstein said is general relativity. But the quantum theory, he said, is opposite, wood. The quantum theory is wood, gnarled branches, leaves, twigs, horrible, this horrible mess called wood. Einstein wanted a universe of pure marble. That was his dream. That was his holy grail, a theory of pure marble. Now, we think that that theory is probably not quite right. We think that the paradigm is music, that music is the paradigm rich enough to explain all the particles of the universe. You see, when a string moves, it vibrates. Each vibration is a subatomic particle, and bingo, that's how we get the hundreds of subatomic particles that we find after spending billions of dollars smashing atoms apart. But among the particles that are moving are the graviton. The graviton is a piece of gravity. And if you calculate the motion of the graviton, it curls space up around it just the way Einstein predicted. So in other words, gravity is for free. Gravity is nothing but one vibration of the string. And like I said, even if Einstein had never been born, we would have discovered general relativity in its entirety as nothing but the lowest vibration of a string. And by the way, the standard model, which represents the subatomic particles of today, can also be embodied in the lowest vibration of the string. And so I think that it's gorgeous without even working too hard at all. Without even working too much, we get relativity for free, and we get most of the quantum theory for free, just assuming that you have string theory.
That's very good. Okay, so now, so in general theory of general relativity predict the gravity is a curvature of space-time. So in your theory, what is gravity?
First of all, when a string moves, it curls up the space around it as it moves because the string is a source term for general relativity. But not only that, it also quantizes general relativity. You see, on this smooth surface, there are ripples. These ripples are called gravitons. Now, we've never seen a graviton before. We think it does exist because if you take Einstein's theory and quantize it, you have ripples on this smooth fabric that we call gravity. And these ripples are gravitons. String theory has both. The gravitons are nothing but one higher excitation of the string. And when the string moves, it curls up the space around it just the way Einstein predicted. So we have this beautiful unification of gravity with music. When string moves, it creates music. One of the vibrations we call gravity.
In your formulation, in your version of field string theory, are you able to predict the gravity correctly, just as general relativity?
That's right. The lowest vibration of the string contains particles with spin 0, spin 1, spin 2. The graviton is spin 2, and it is just nothing but one vibration of a string. String has many spins, among them spin 2, and a massless particle of spin 2 is the graviton. And the graviton in turn is a ripple on the surface of curved space-time, which string theory also incorporates. So string theory incorporates not just Einstein's theory, it also embraces the quantum version of general relativity. And that is the holy grail of modern physics, to unify the left hand and the right hand, to unify relativity with the quantum theory. That's what string theory does, because each vibration of the string is a quantum vibration, but when the string moves, it forces space-time to curl up just the way Einstein predicted. And all of this is for free. You don't have to do any work. It just pops out of the equations. It's the most amazing thing. Without any prodding, the theory naturally gives you all of Einstein's theory and the quantum theory. This, to me, is amazing, absolutely amazing, for free.
So in your theory, gravity still the same as a curvature of space-time. Is that right? So
yeah,
basically
plus,
the same thing.
Yeah, plus it gives you the corrections to that as well. String theory gives you gravity as a curvature of space-time, plus it also gives you the graviton, which is the quantum version of general relativity. It gives you both. It gives you both the classical theory if you want, but it also gives you the quantum theory, all for free. It's built into the equations. You have no choice. Even if you don't like gravity, string theory forces you to have gravity.
So in the quantum field theory, that basically the quantum version of gravity, so they missed by the gravity, what we observed, by what is exponentially, many magnitude. So in your theory, so what's the difference? So how did you correct quantum field theory in your theory? So you get a correct prediction.
Well, let's talk about dark matter and dark energy, because that's what I think you're alluding to. The Milky Way galaxy is surrounded by invisible matter called dark matter. If I had it in my hand, it would be invisible. In fact, it would just sift right through my fingers as if my fingers weren't there, go right through the earth and go to China. And then in China, it would reverse direction and come back to New York City. And then it would oscillate between New York and China. That's dark matter. It turns out that we think that dark matter is the next octave of the string. We are the lowest octave. We're the lowest vibration of a string. But the string has many, many vibrations and octaves beyond that. In fact, an infinite number of vibrations beyond that. The next set of vibrations includes a particle called the photino. The photino has a mass, but it has no electromagnetic charge. It is invisible and it is stable. That's exactly what you want for dark matter. So string theory, we think, actually predicts the existence of dark matter. Right now in this room, there's dark matter going right through your body. Right in your living room, there's dark matter. We live in a wind of dark matter, but it's invisible, hard to detect, so we don't even know it's there. But one day we will detect it with our machines. A spark chamber may eventually detect it in a laboratory any day now. We have many groups looking for dark matter in the laboratory in a spark chamber, and then we will prove the existence of dark matter, which we think is nothing but the next higher vibration of the string. Another musical note.
Well, that's very good. So you are trying to explain. So now let's come back to the fundamental, we say the elements in your field string theory is a closed loop string or just a string of string? What is that? The fundamental form of elements.
The fundamental element is a vibrating string. It's a closed string and an open string. There's two kinds of strings. Okay. You can break a string and it becomes an open string. But gravity, we think, is part of a closed string. And when these two strings bump into each other, they form a bigger string. And that, we think, includes all of general relativity. You can discuss the scattering of gravitons this way. And so we have a quantum theory of gravity. Now, why do we need a quantum theory of gravity? We want to know where the Big Bang came from. Why did it bang to begin with? You see, the present theory simply says the universe had a bang. That's all Einstein's theory says. There was a bang. It didn't say why there was a bang, how it was a bang, why did it bang when it banged? Nothing. That's what string theory will tell us. It will even tell us what happened before the beginning of time. We think the universe is a bubble. We live on the skin of the bubble, and the bubble is expanding. That's called the Big Bang theory. String theory says there are other bubbles out there, other bubble universes in a multiverse of universes. And when these bubbles touch each other, boom, that's the Big Bang. The Big Bang, we think, is either the collision or the fissioning of universes. And so when these universes collide, we get a bigger universe. And that could be the Big Bang, parallel universes. And then the next question that I often get is, if there are parallel universes out there, then is Elvis Presley still alive in another parallel universe? And the answer is possibly yes. Yes, the king could still be alive, belting out hit after hit, but in another parallel universe. Not for us. In our universe, he died. But in other universes, other quantum universes, he could still be alive.
Yeah. What is the in the Big Bang? What is the universe expanding into?
Well, that's what children ask. They say, "Mommy, Daddy, if the universe is getting bigger and bigger, what is it getting bigger into?"
Yeah.
And the answer is it's getting bigger in a higher dimension. We live in a three-dimensional world. The skin of the bubble is three-dimensional, but it's expanding in a dimension perpendicular to the other three. In other words, the fourth spatial dimension. How many dimensions are there? String theory predicts up to 11 dimensions. And so these are bubbles floating in 11-dimensional hyperspace. When they bump into each other, that gives you the Big Bang. Now, this has implications for me as a child. You see, when I was a child, I knew that my parents were Buddhists. In Buddhism, there is no beginning, there's no end, there's nothing but timeless nirvana. But I was raised as a Presbyterian. I went to Sunday school every week, and I learned about Genesis, that the universe had a beginning. So either the universe had a beginning, or it didn't, right? No two ways around it. Wrong. There is a way to blend these two theories together. You see, our universe had a beginning. Our universe had a Big Bang, but there are other universes out there. In a multiverse, a bubble bath of universes. And what are these universes expanding into? What are they floating in? Nirvana. And what is nirvana? 11-dimensional hyperspace, a dimension beyond our feeble comprehension. And when I was a child, I used to go to San Francisco to the Japanese tea garden. And I used to spend hours looking at the carp swimming in 2 dimensions. And I asked myself, what would it be like to be a fish? You would only know about 2 dimensions. You could swim forward, backward, left, right. But anyone who talked about a higher dimension would be considered a crackpot. Crazy, nonsense. There's no 3rd dimension. There's only the pond. And then I imagined grabbing one of the fish, a scientist fish, who said, bah, humbug. There's no 3rd dimension. Lifting the scientist into the 3rd dimension, what would he see? He would see beings breathing without water, a new law of biology. Beings moving without fins, a new law of physics. Well, believe it or not, today, many physicists believe that we are the fish. We spend all our life in 3 dimensions. We go forward, backward, left, right, up, down. But anyone who talks about a higher dimension is considered a crackpot, an idiot, until now. Now we think that the arena, the true arena of the universe is hyperspace. And we are nothing but on a bubble floating in nirvana, timeless nirvana.
So the universe is infinite then, if this hyperspace is the universe, right?
That's right. If hyperspace is the universe, then it's infinite. But the bubble, Each bubble is finite, we think. But again, this is still speculation. We're not positive.
So based on this multi-universe theory, that's apparently is part of your prediction.
Right.
So you do not believe a Big Bang is
No,
the
our
beginning.
universe had a Big Bang, but
What
there are
about
other universes.
What about all the universe in general? So we use a term. So say,
Well,
all
there's
universe
continual, see, quantum theory simply says there's a finite probability for things to happen that are unlikely but possible. To have multiple Big Bangs, even as we speak, to have universes being created even as we speak right now is well within the laws of physics. You just have to wait long enough. And that's what we think is happening. Once you quantize gravity, then you are forced to admit the possibility of alternate universes. See, when we quantize the electron, what do we get? Parallel electrons. And what does that do? That gives us a laser. Why do we have lasers? Isaac Newton would say that a laser is impossible. No way that a photon could be two places at the same time. Well, get used to it. Electrons can be two places at the same time. But if we quantize the universe now, and the universe is a bubble, that means the bubble can be many places at the same time. And that's the multiverse idea. When you quantize the entire universe, you have to admit the possibility that there are other universes out there. This is forced upon you. You have no choice.
So based on your explanation, so space existed and the time existed before Big Bang.
Yeah, hyperspace. Hyperspace existed before the Big Bang.
Oh. Okay, so that's a different than the Big Bang, original Big Bang theory.
Yeah,
so, yeah.
And that's compatible with all the data. All the data supports the inflation theory, and the inflation theory is based on the idea that the universe can inflate many times, and the infinite cycle of Big Bangs happening all the time.
Does hyperspace has a Big Bang event?
Yeah, in hyperspace, universes are continually being created. They're making a quantum transition to another energy state.
Okay, so you believe hyperspace also created by Big Bang event, is that right?
No, hyperspace is beyond time. See, time is nothing but just one dimension. Hyperspace is beyond that. Hyperspace is 11-dimensional hyperspace. And time is just one dimension among the other 11 dimensions.
Yeah, which is actually quite similar to conventional philosophical concept of infinite universe and infinite time. I agree with this kind of origin. Okay, so let me ask you. So after you created, you're one of the founder, or you're maybe the founder of field string theory. So in your deep mind, do you feel like you understand how universe works?
How the universe works? Well, just realize that the theory is smarter than we are. We are discovering new aspects of string theory all the time that shocked us. You see, we were not supposed to see this theory in this century. By accident, we discovered this theory. I like to think of it as walking in the streets in the sands of Egypt. And when walking in the desert, you trip on a tiny pebble. And then you brush away the sand, and you realize this pebble is the top of a pyramid. And over decades of work, you find new excavated chambers, hidden hieroglyphics, strange markings, all sorts of strange things indicating a higher intelligence. Finally, you're at the bottom. Finally, you're at the bottom of the pyramid, and there's a door. And we are just now about to open that door to find out where this pyramid came from. You see, this theory was discovered by accident, purely by accident. It was not supposed to be this way. Usually scientists discover something by experiment. Nope. We were thumbing through a math book, and all of a sudden, boom, the Euler beta function popped out, which describes the scattering of pi mesons. So why should pi meson scattering be described by a mathematical formula of the 1800s? Later, we found out that the formula worked because it was the collision of two strings, and that began string theory. So this theory is smarter than we are. Mathematicians are desperately trying to learn about string theory. If you want to win the Nobel Prize in mathematics, that's the Fields Medal, you pretty much have to know quantum field theory and string theory. Many of the Fields medalists were inspired by quantum field theory and by string theory. That's how powerful this theory is. Usually mathematics comes first and physics comes later. Here's the opposite. Here physics is coming first, and the mathematicians are desperately trying to catch up to the rest of physics.
Yeah, that's right. Okay, so what's the string made of?
Well, the closest thing you can say is a string is made out of pure energy, because it is that which everything else is made of. And so you cannot really say that it's made out of wood or made out of plastic, because wood and plastic in turn are made out of strings. So this is the substance out of which everything else is made of. But the closest you can come is pure solidified energy.
What's your definition of energy?
Energy is the ability to move objects. And that's why we measure it in terms of force of motion, ergs and joules, the ability to move objects. Now, string theory has an energy associated with it. It's called the Planck energy. The Planck energy is the energy at which modern physics collapses and breaks down. It is the energy of the center of a black hole, the energy of the instant of the Big Bang. It is 10 to the 19 billion electron volts. That is a quadrillion times more powerful than the Large Hadron Collider, which is the most powerful machine of science that we humans have been able to create. Physics at the Planck energy is totally different from energy of today. At the Planck energy, space and time become unstable. If I had a super microwave oven, and I could heat empty air to the Planck energy, eventually, not just water would boil, space begins to boil. The integrity of space itself collapses at the Planck energy, and bubbles begin to form in your microwave oven. Each bubble is a baby universe connecting you to another universe. You see, we think that we will eventually have pictures of the baby universe as it emerges from the womb. We have a satellite called LISA, Laser Interferometry Space Antenna. The European Space Agency and NASA are pushing it. And we're going to get baby pictures of the instant of creation as it emerges from the womb. And then we hope to find evidence of an umbilical cord connecting our infant universe, our infinite baby universe, to a mother universe. Because this is the multiverse idea. It is a testable idea. Gravity wave detectors in outer space could give us baby pictures of the instant of creation. And maybe, just maybe, give us evidence of an umbilical cord that connects our infant universe to where it came from, a mother universe.
Yeah, you alluded to the testable. So you think the multiverse, and you mentioned about the parallel universe. So these are all testable?
That's right. Let me give you five different tests of string theory. First of all, 1 month ago, outside Chicago, Fermi Laboratory found a deviation, a crack in the standard model. The standard model is a messy, ugly model, but it works at the low energy realm. Nobody thinks that it works at the high energy realm beyond 14 trillion electron volts, but below 14 trillion electron volts, it works perfectly fine until last month. Last month, we found the first major deviation in the standard model, meaning there could be a fifth force beyond electromagnetism, beyond gravity, beyond the two nuclear forces, a fifth force that could be string theory. It could be the next octave of string theory right before our eyes. Second, dark matter. As I mentioned, there are many groups, about 20 of them around the world, looking for the presence of dark matter in the laboratory. Once we find dark matter, we can then compare it with predictions being made by string theory. Number 3, LISA, Laser Interferometry Space Antenna, means that we'll have photographs of the infant universe as it emerges from the womb. And maybe we'll have evidence of a parallel universe connected to our baby universe. And 4, The Chinese, the Japanese, and the Europeans are now looking for the next generation of particle accelerators beyond the Large Hadron Collider. The Large Hadron Collider is old and it has to be replaced. So the Japanese, Chinese, and the Europeans are making proposals for the post-Large Hadron Collider era, but we may pick up sparticles. Sparticles is the next generation of particles. And then 5, deviations from Newton's laws of motion. We know that Newton's laws of motion works for galaxies, but does it work in your living room? We don't know. It's never been tested really at a small level. We only test Newton's laws of gravity at the solar system level, not in your living room. And so if there's a slight deviation in the inverse square law, it means there could be a 4th, 5th, or 6th dimension, very small, but measurable inside your living room. And so anyway, these are 5 experiments that are ongoing, 5 ways in which we can test this theory. And one of them is happening right now in Chicago, as people are wondering what is causing the mu meson to have such an erratic magnetic moment.
That's right. And what's your answer to that deviation from standard model? What's your explanation?
Well, I think that the standard model is just nothing but the lowest octave of the vibrating string, and there are higher octaves, because why should Mother Nature create a theory so ugly? It has 36 quarks and antiquarks, 3 identical generations of subatomic particles, 20 free parameters. It's a mess. It's a theory that only a mother can love. Even the creators of the standard model believe that at low energies, it works fine, but at high energies, it must break down. There's got to be a higher theory, which is more beautiful than this ugly theory called the standard model.
So you do believe a standard model is not fundamental?
It's a theory of almost everything. It's a theory of the lowest octave. That's it. But they're higher octaves.
So that's where there's so many observations is different than the standard model can describe. So you think your string theory and include all of this phenomena?
Well, as Carl Sagan used to say, extraordinary claims require extraordinary proof.
Right.
The proof could come out of Chicago, as we find out why the magnetic moment of the muon came out incorrect. The logic is that there's a new particle there, a new particle mediating a new fourth. A 5th force may be unraveled outside Chicago. And string theory provides a catalog of particles beyond the standard model. The standard model is just nothing but the lowest musical note. They're higher notes. And that's what we hope to prove with this new result that is only 1 month old.
Yeah, that's what is the muon G-2 experiment, right?
That's right.
And also confirmed with the CERN's, particle accelerator experiment. So somehow
this is big news. The first crack in the standard model, which we know is an ugly theory, but it could be just the beginning of this whole new series of subatomic particles given to us by the music of subatomic particles, higher octaves.
So now I want to ask you some general questions about it. So how many fundamental forces based on string theory?
Well, if you calculate all the different particles predicted by string theory, they're an infinite number. How many vibrations can you make on a guitar, a violin? Infinite. There are an infinite number of notes you can create on a violin simply by going to higher and higher octaves. Same thing with string theory. There's an infinite number of particles, but there's only one string. There's one string, but an infinite number of notes that you can make on that one string.
I agree. We are not just limited, just to say what is 25 or 26, some fundamental particles. We have a lot more. Okay. Oh no, we are not just a lot more. So basically, you said we have infinite.
Infinite number, right?
Infinite number, but the force. Now I'm talking about the force.
Yeah. So far we have 4 fundamental forces, but the 5th force may be discovered outside Chicago. But there could be a 6th, 7th, and 8th force, because string theory just keeps on going on forever. It's just music.
So what is the force in string theory?
What is a what?
What is the force in string theory? How
Well,
things interact?
Well, Newton gives us the idea of a force. The quantum theory says what mediates the force. What mediates the force is a particle. But now we have so many particles, it's hard to believe that that is fundamental. And so string theory explains why there's so many particles, but each particle in turn mediates a force. When a particle bumps into something, it gives the illusion that there's a force involved.
If a particle does string, okay, so your particle, how could a particle, so without any force interaction, you mean the interaction of particle?
No, a violin just by itself makes musical notes independent of an orchestra. You don't need an orchestra in order to look at the vibrations of one violin string. Now, with an orchestra, of course, you can make beautiful music, much more than just with one violin string. But the same thing with a subatomic particle. A subatomic particle is like one violin, and reality is an orchestra, which we call a molecule. And molecules, in turn, make up the universe.
So the difference between gravitational pole, and versus electromagnetic, interaction. So how do you differentiate this?
Yeah, the electromagnetic force or light is mediated by the photon. A photon is a quantum of light. A particle of light is called a photon. In fact, it was Einstein himself who first introduced the concept of the photon in 1905. The gravity is the same. You chop up gravity. The smallest unit of gravity is the graviton. It is a particle. It has spin 2 rather than spin 1. It is massless. And when gravitons bump into each other, they can reproduce all of Einstein's theory of general relativity without Einstein. And like I said, you don't need Einstein anymore when you have string theory, because the only self-consistent theory of an interacting spin 2 particle is general relativity. General relativity would have been discovered anyway, even without Einstein. Now, of course, Einstein was ahead by 100 years. He beat everybody. But even without Einstein, we would have gotten all of general relativity with string theory. That's the power of string theory.
See, we also have a strong nuclear force and the weak nuclear force. You mean all these 4 different fundamental forces based on the current theory can be explained independent of string theory, or it is part of is part of explanation of string theory?
Well, we have 4 fundamental forces. We have gravity, which keeps us on the floor. We have electricity and magnetism, which lights up our cities, gives us dynamos and generators. And then we have the 2 nuclear forces. All 4 forces are part of the standard model, which in turn is nothing but a vibration of the string. So string theory includes the 4 fundamental forces. Not only that, it goes even beyond the standard model to give particles which may explain the result coming out of Chicago just a few weeks ago. So the nuclear force is mediated by quarks. Quarks are nothing but another vibration of the string. If I have a super microscope and compare it into an electron, most people would say the electron is a dot. Nope. String theory says the electron is a rubber band. And when it vibrates like this, we give it a name. We call it an electron. When it vibrates like this, we have to give it a different name. We call it a quark. Quarks in turn mediate the strong nuclear force. So here's the electromagnetic force. Here's the strong nuclear force. And all the forces are nothing but little vibrations in a rubber band. Very simple.
Yes, mechanism. So I would know, how could the vibration create different forces?
Simple. These vibrations in turn bump into other particles and they exert a pressure on these other particles. And that pressure is then measurable as a force. So forces are a byproduct of particles bumping into each other. For example, why am I sitting on this floor right now? Well, gravity is apparently pushing me down, right? But there's a force, the force of gravitons pushing me down into the floor. And so we see that particles mediate forces.
Yeah, which is quite similar to Newtonian force.
Yeah, but
due to impact.
Newton does not predict all the forces. He just explained one force. String
That's right.
theory predicts all the forces and more.
Okay.
Predicts a new generation of forces.
How do you explain? So you just explanation bumping each other. I can see create called a tensile force, attract called a repulsion force. You're bumping each other.
These particles bump into each other, and that creates force. That's how forces emerge.
How do you create attractive force?
Well, the same thing. Forces can either be attractive or repulsive. It all depends on what happens when two particles bump into each other. That's all.
So you do have a force existed in the string before you formulate the string. Is that right?
Industry? I don't understand what.
No. You do have a force as existed with the energy, with the string. The attraction force. Where does the attraction force come from?
Well, let's say the difference between force and particle, okay?
Yes.
Force is what moves other objects. Matter moves because they're hit by a force. The question is, in the quantum theory, why is an object being hit by a force? It's being hit by a force because it's being hit by particles, quantum. For example, electricity and magnetism is a byproduct of the electromagnetic force, which is mediated by photons. A photon is a spin 1 particle. Gravity is spin 2. They're both massless. And when a photon bumps into you, it gives you light. That's what we call light. When light hits the retina of your eyeball, a photon hits your retina, causes your retina to fire, and that's what we call light. So force is a byproduct of particles. Particles, in turn, we think, are nothing but musical notes on a string. So what is the origin of force? The origin of force is nothing but string theory.
And the string theory based on the vibration of a string of energy, right? So force is created by the vibration of a string?
Yeah, that's right.
Okay. So in your theory, so fundamentally, it's only the so-called force or the number of particles. It's just a string of vibrating string. Is that right?
That's right. The universe is a symphony of vibrating strings. And that's how we have a unified theory of the entire universe based on music. The universe is one gigantic symphony.
Okay. So now I wanted to you explain. Do you know what is what is the electron?
The electron is nothing but one vibration of a rubber band. The lowest vibration of this rubber band we call the electron. But if you twang it, it has higher vibrations, like the quark, like the neutrino. They're nothing but different vibrations of the same string. We call it a different name because it's vibrating in a different way, but it's the same string.
You would be able to explain the different generations of electrons, right?
That too. The mu1 is nothing but a higher generation of the electron. That's being studied now outside Chicago. That too is part of string theory. See, string theory includes the standard model as one of its solutions. So the standard model, and billions of dollars have been spent creating the standard model, billions of dollars. All of that can be explained in the language of music.
Wow.
Okay, so where comes the charge of electron charge?
Yeah, what about the electron charge? That is a byproduct of the electromagnetic force. The electron interacts with a photon, and that we call charge. Why do charges move? Charges move because the photon bumps into the electron and causes the electron to move, and that's what we call the electromagnetic force.
So in this case, electron, you do believe it is a negative charge or it is a bipolar charge?
Well, the electron has negative charge, but the positron has positive charge. And so we have antimatter with the opposite charge of ordinary matter, but the electron has negative charge. And we call it negative charge because of Benjamin Franklin. We could have called it anything we want, but Benjamin Franklin said this is the charges go from one electrode to the other electrode. It was arbitrary. And that's why we're stuck with electrons being negatively charged because of Benjamin Franklin.
Okay, so so how do you explain? So what is electricity for in your case? In your
Well, electricity is nothing but the motion of lots of electrons.
Is traveling through physically traveling through conducting wire?
Yeah, that's one
Okay.
way to do it, right?
Oh,
You can
okay,
also
so-
do it in empty space. Electrons can move in empty space. That's called plasma. So a lot of the plasmas in outer space is moving electrons.
Okay.
Anyway, the point I'm getting is that all of this can be explained in terms of string theory. All of it.
Wow.
Everything we talked about tonight can be
Wow.
explained in terms of string theory. Name one thing. Name one thing that is outside string theory.
One thing I feel, there's might be some much more simpler explanation to all this phenomena.
Well,
So
remember,
that's what people looking for, a single theory based on the single principle or even single particle, single force to describe everything in the universe.
well, I tell people that if they ever discover the God equation, what should they do? They should contact me and tell me first. Tell me first, and we'll publish together, and we'll win the Nobel Prize together.
Okay, so somebody might be might be able to do that one. So okay. One thing I have a different interpretation with all the phenomena we just mentioned about, Big Bang, black hole, dark matter, dark energy, and even the fundamental form of matter. So in your case, the fundamental form of matter is a strain of vibrating energy, right? So,
Yeah.
There's another explanation for me is more intuitive, and it is also can correlate all the phenomena we mentioned. Is use a single it's called a single particle theory of everything. So basically, everything we made of just by single particle and with a single force. So it has the particle we mean it has a matter in it. It's not like energy started with no matter because vibrating create energy and mass equivalent. No, in other words, the matter, the universe only exists the matter and the void, of course, space and time. So the matter, the fundamental form of a matter is actually magnetic particles.
A lot of people email me saying that they have the God equation. And I tell them that to qualify for the God equation, you have to have three things. First, it has to include of Einstein's theory of gravity. You have to have general relativity inside it. Second, at least the standard model, maybe beyond, but at least all the quarks, leptons, 36 quarks and antiquarks, 3 generations of particles, 23 parameters. That has to be inside your theory. And third, it has to be finite, anomaly free, free of divergences, mathematically consistent. So far, after hundreds of years of working on this, physicists have only come up with one solution. Just one solution that includes relativity, includes the standard model, and is finite, and that's string theory. All other proposals have been shown to be either incorrect or missing the standard model, missing relativity, or not being finite. So if you want to win the Nobel Prize, your theory has to satisfy three things.
It can be satisfied, just like you said, just one piece of string, vibrating string, can satisfy everything, right? Of course,
That's right.
One piece of a material matter particle with a magnetic field is a part of the particle. It can explain everything and much intuitively and much logically.
Well, write it up, publish it, okay? And, Physical Review, D, Nuclear Physics, B, these are all reputable magazines, and that's where we publish. We publish in Nuclear Physics B and Physical Review D. That's where we publish. So write it up, publish it, and we'll see how it goes.
Yes. That's very good. So I just want you to know, see, if we assuming, so electron, so in my mind, the electron is actually not a negative charged particle. It's actually just a little magnetic particle. It has both positive and negative charge, possible and negative magnetic field. And by doing that one, so the next logical derivation, the next logical step was if an electron is not a single charge, is actually a multiple charge. So then everything built by this fundamental particle, magnetic particle, electron, or all the particles in quantum mechanics is just a composite particle.
Well, like I said, you should write it up and submit it to Nuclear Physics B or Physical Review D magazine.
Yes.
And there are referees, people like me, who will read your paper and say, yes, no, should it be published? Okay.
Dr. Kaku, I want to ask you, we're going to be interviewing Lou Elizondo, the guy who came out as the whistleblower for the Pentagon's ATIP program, the Advanced Aerial Threat Investigation Program, which was their look at unidentified aerial phenomenon. Here's someone who was collecting data, appointed this program by Senator Harry Reid, who was then Senator, Majority Leader at the time the program was created. They're about to release a report next month in June describing what the government has been collecting in this program. He got out as a whistleblower because he felt like the bureaucracy wasn't taking this threat seriously enough. He thought it would, if you have something, the way he describes it is, if you come into the house in your house and you've got all the doors locked, but you still see muddy footprints in the living room, that could be a problem. And that's what we're seeing. We have things that are going past our ability to detect them before they're in our airspace. What would you say to this topic? I mean, this is something you've been talking about for years, and here's your own government about to disclose allegedly everything they know about this, and they're taking it very seriously finally.
Well, let me say a few things about that. First of all, I get a lot of emails from people saying that, well, I'm wrong. I'm wrong because the aliens are not up there. The aliens are here. The aliens visit them. And I say, well, how do you know? And they tell me that, well, they've been kidnapped. They've been kidnapped by aliens and they've been in their flying saucers. I have a word of advice. The next time you are kidnapped by a flying saucer, for God's sake, steal something. A pen, a chip, a paperweight, anything alien, steal it. There's no law against stealing from an extraterrestrial civilization. No law whatsoever. You're not going to go to jail.
At least get a t-shirt, right?
And you'll get proof. You'll be able to go to the newspapers and say, I got proof, an alien chip. End of story. End of story. Ends all the speculation right then and there. Let me also say that we physicists have taken a look at, frame by frame, the US Navy pilots' videos, and we've clocked it now. We can now measure it because science is based on things testable, reproducible, falsifiable. And we've clocked it now, frame by frame. We know they travel between Mach 5 and Mach 20, which is the range of hypersonic drones. Hypersonic drones can also fly between Mach 5 and Mach 20, up to 20 times the speed of sound. And the G-forces are so great that it would crush the bones of any human. So these are probably drones of some sort that can execute these zigzags. So you can't rule out totally that they're not hypersonic drones. The Chinese, the Russians, and the Americans have admitted now that all three are working on hypersonic drones. And the Russians even claim to have a model that's operational. Putin was boasting about that fact. We canceled our drone program 2 years ago. And so now the administration is furiously trying to catch up to the Russians. So that's a possibility. The other possibility is that they are extraterrestrial because they move at the cutting edge of known technology. Now, the fact they zigzag is not so surprising because that's what hypersonic drones do. Why are hypersonic drones being investigated at all by the government? Precisely because they zigzag. And that means they can evade a Star Wars anti-missile shield. That's why all of these drones zigzag. But the zigzagging does not cause a sonic boom, which is very unusual. Anytime you have a disturbance like that, you would create a sonic boom. And we see no sonic booms there. So in other words, the point is that, well, either they are hypersonic drones or or they are extraterrestrial. And
then
I
what
think
about
the
them
burden,
being
yeah.
transmedium, where they're able to go underwater? We just saw that video the government just acknowledged come out where the thing dips into the water, which has been described by Lou Elizondo. Apparently, this is happening a lot, and it's happened at the Nimitz encounter, which was documented by many different highly qualified military personnel from different ships. So it's going underwater. Does a drone? Do we know that hypersonic man-made drones could possibly go underwater and come back up and transmedium travel like that?
Not to our knowledge. That is not a priority. The priority for the hypersonic drone is to evade a Star Wars anti-ballistic missile shield, not necessarily to go underwater. But let me say a few more things about that. If they are extraterrestrial, then their technology is way beyond what we can easily muster here on the planet Earth. And then the question is, how come they don't visit us? How come they don't introduce themselves and say hi? Well, if you're wandering in a forest and you meet a squirrel, do you go down to the squirrel and talk to it? Well, maybe initially, hi there, but eventually you get bored because the squirrel doesn't talk back to you. In fact, the squirrel has nothing interesting to tell you at all. And so you walk away. Either you create a zoo or perhaps an endangered area, or you simply leave it alone. So that's why I think that if there are extraterrestrials, we are not on their radar screen. They would probably observe us just like we observe the deer and the squirrels and the forest animals, but they have no interest in talking to us because what do we have to offer them? Like gold? Gold is useless to them, right? Water, minerals? No, they can mine Mars or uninhabited planets, right? We have nothing to offer them. So I think for the most part, they'll probably just leave us alone. Just like we leave.
Hypothetically, if you were ever to meet one of these, if these things are from another planet, whatever this is, AI or what have you, what would you ask them? I have a feeling it might be about string theory, but perhaps you have another question you would ask first.
Well, they are probably a few thousand years ahead of us in technology. If they can go between stars, the distance between stars is measured in hundreds of light years, thousands of light years, trillions upon trillions of miles, which put them as what we call a type 2 or maybe a type 3 civilization. We are type 0. We don't even rate on this cosmic scale of civilizations. So if we bump into a type 3 civilization, we really wouldn't have much to talk to them about. But if they did want to talk to us about these things, I would ask them about the Holy Grail. I would say, do you finally have the God equation, the equation of all equations, the Holy Grail of science? And they probably said, oh yeah, we did that thousands of years ago.
They're going to pull out a guitar and say, here's your strings, right?
Yeah.
Well, hey, it's been a real pleasure to speak with you. I don't want to take up your time. I know you're very busy, but our radio affiliates will enjoy this show. This is going to get a lot of interest, as it should, because you're dealing with the big fundamental questions of our time. So
yeah, this is the biggest question in all of science.
Yeah, and what more exciting time than our own government? Again, suppose it's just drones, but this is extremely interesting technology. If it's just drones, if they can go underwater and come back into space, so what a time to be alive in science, huh?
Right. Yeah.
Well, thanks again, Dr. Kaku. I really appreciate your time. I want everybody to check out your new book, The God Equation, which is out now, and it's already New York Times bestseller. It will continue probably selling quite a bit in this time of science investigation. Thanks again.
Okay. Thank you.
Thank you.
Thank you.